Hello again. In the last video, I said that we have upgraded SWATCUP-Premiun to version 6.2 and SWAT Plus Cup to version 3.0. And also in the last video, I showed you an example of SPE, how to build the project and go through the different steps of calibration. The last video took a bit longer than I had anticipated because I explained in more detail every step. So in the next video, I'm going to show you PSO, and this is going to be a much shorter video because the explanation for PSO and SPE as far as the calibration is concerned is exactly the same, and the input files with like one or two exceptions are also exactly the same. So you could easily switch between SPE and PSO. So let's start the program here. Similar to SPE, we can start a new program or open an old program. So let's build a new program. Look for texting out. Next, identify the problem we want to use, the algorithm PSO. Give a name, call it test, and find the folder to save the project. Now all the files are being copied, similar to before. Let's have a look at the project, test PSO, and these folders are exactly the same. There is the backup, which has your text in out and echo and iteration, then input and output. You notice there is no parallel processing because with PSO, we cannot have parallel processing. PSO is, with SPE, we could sample all the parameters at the beginning and then run them one at a time. That's why we could have parallel processing, but with PSO, the next iteration depends on the best parameter set of the previous iteration. So that's why we cannot sample them in advance. Therefore, there is no parallel processing. Everything else is exactly the same. And here at the end, you have all the PSO related files. Now, there are two main differences between PSO and SPE. One is that because you cannot sample all the parameters at the same time. You have to combine iteration and simulation in one run. So it is not as sequential as SPE. Therefore, in the parameter information file, you have to define the number of simulations as well as the number of iterations. So in each iteration, in this case, 10 simulations are performed, and then the next iteration is also 10 simulations are performed, and the parameters, the best parameter of the first iteration is given to the next iteration, and the next iteration begins. And then the best parameter is given to the third iteration, and that one begins. So it has such a format. You have the weight here, you have to define a weight. In the velocity calculation, what that means is that the larger the weight is, the more expanded is the space where the program can search for a parameter. So the larger becomes the uncertainty band of the parameter where it can look for a value. And the smaller it is, of course, the smaller is the domain of the parameter space. And then this optionally I added, that means if you make a run at the beginning, because initially the parameters are chosen randomly, but maybe you want to make a smaller run and then choose the best parameter of this run and start a new run altogether using, so if you put this to 1, it will use the best parameter of the previous run. And then from here on is exactly the same as SPE. You have the number of parameters and you can go through exactly the same procedure. Initially, you take a dummy parameter and you look at your model simulation, the initial simulation. If it is relatively okay, you can calibrate it. If it is really off, then you better look at the the model and don't try to calibrate that. Everything else is exactly the same. PSO is always behavioral, so that's why we don't have here behavioral simulations. We only have single objective and multiple objective, as it is also shown here in the outputs. You can have only single objective or multiple objective. So at the beginning, you have to decide to run one or the other. You cannot make a run and then run the post-processing for single and objective case because of the fact that, again, as I said, the next parameter depends on the previous parameter set. Otherwise, everything else is exactly the same. So I can make a run and show you the results of this. So what I can do is I close everything and then with calibration, do a pre-processing of PSO. And then after that, you can decide on either single objective run and then its post-processing or multiple objective run and its post-processing. And of course, there is no observation here. So let's just quickly to see what we are extracting. And what we are actually the best place to go is in the execution batch file and PSO extract. Now here I'm only extracting files from reach, and I'm also extracting no observation from reach. As you see, the format is exactly the same as before, the same with all these batch files. So that's what I'm doing. So let's start a run. Now, okay, at the beginning here, you will notice that it's going to give me an error. You see the SWAT is not being run. So it's the same issue as in SPE. There is no SWAT execution for the new parameter and the first run. So I have to get an execution file. So I go to the project because I have already built the SPE. I'm going to grab SWAT exe from here. You have to get it from your where you have built from the ArcSWAT folder, and then I copy it into the PSO here, and I start again, calibration, pre-processing. Okay, so just let's make a run here, and this is going to do 80 simulations, so I'm going to pause the video, and when it's finished, I will continue. All right, the run is finished, so I will then go to the next step, which is post-processing. And then we can go through the outputs as before. So I only have single objective outputs to look at. So we get the 95 PPU. Here I only had two variables. I had nitrate from subbasin number 16 and discharge from subbasin number 16. And then the dotted plots are similar to before. Here again, you see the strong dependency on CN2. So CN2 is a very sensitive parameter and not these so much, maybe a little bit of soil water content. And maybe there is a trend here in revap MN. Maybe there is a trend downward here in revap, and then so on. As I said before, dotted plots are like visualization of sensitivity and really give you a good feeling that as CN2 increases, your objective function, which is here Nysath-Cliff, also increases. And then you get the chain. This is the evolution chain of objective function. So that's how it is as samples are taken. So it improves, it goes down, it goes up. And as I said, you need here much more, many more simulations than in SPE. Here I would set anywhere from 1,000 to 3,000 simulations. You need a large number of simulations to get the best parameter set. And then there is the goal function as before. So you have simulations here, iterations are here. This is simulation number. And then you get all the parameters and finally the objective function here. So as I said before, you can really do a lot of analysis with this information given here. And then you have the summary stat as before. For every variable, we have the p factor, the r factor, r squared, and so on. And this is the most important information here is the p factor and the r factor, and I have discussed this quite a bit before. And I've recently published a paper that I really recommend that you read this paper or have a look at it, because I see a lot of people are after the best objective function value. They try to get the best Nice-Sutcliffe. That is not really ideal because Nice-Sutcliffe is based on only one simulation, albeit the best simulation. You have many other simulations that are as good, and you can see that in the goal function here. I really suggest that you do this. You sort on the goal function here, and you see that the best parameter set, the difference between the best parameter set and the next best parameter set is really negligible. So that means if you have one good simulation, you have hundreds of thousands of good simulations, and you cannot just take the parameter set associated to the best objective function value and say that is the solution to the problem that you're trying to solve. To make this point, I wrote this paper, and I recommend that really you read it and don't go after Nice-Sutcliffe so much, but you need to look at the p factor and the r factor, and I've explained this in detail in papers and previous videos. P factor is the percentage of the observed your observation in the 95 PPU band. Those are the ones that you are, with your parameter set, you are accounting for, or you are capturing those observations. So here we are only capturing 24% of our observation. This is obviously not very adequate, even though it could have a very high Nice-Sutcliffe. For one of the simulations could have very high Nice-Sutcliffe. Still, that is not a very dependable model. And R factor shows you the uncertainty, and 1.6 is a bit too high, as you can see probably from the 95 PPU. So you need to decrease the uncertainty and increase the P factor, and I've discussed this a lot of times in previous videos and so on. So I'm going to give you the link or the reference to that paper at the end of this video. But that's really that's the whole thing I can say. I have explained everything before. You can do exactly the same thing with multi-objective function. Now there is one catch here. Multi-objective function, if you recall in SPE, we did the post-processing, we looked up the weight, we changed the weights of the objective functions, and then we ran the post-processing again, and that took like less than a minute to do all these. But in PSO, we cannot do that, because if you do 2000 simulation, that's going to take a long time. And then you cannot wait for that and then get the weights and then run it again. This is going to take a long time. So there are two solutions to that. One is that you make a small run, you get the weights, and you put the weights in where they should go in the observed value here in the observed file. You put the weights here, and you for the small run, and then you make a larger run. This is one option, which is right now available in the program that we have uploaded. The second is, which we haven't uploaded yet, is that it will come in the next version. It will come soon in the next version. What you can do instead of building the objective function, let me open the manual, then I can explain it a bit better. Right now, the multiple objective function looks has such a format. It has such a format that it's a combination. It can be a combination, a summation of 11 different. Uh, sorry, let me find it here. So the multi-goal can be any combination of these 11 performance indicators, right? It can be any combination of these. And this by itself is quite interesting to explore, I think. But you can have a multi-objective function such as the one here, where you have a weight multiplied uh, by the respective performance function. And these weights are important because the values of these can be very different. I mean, R squared is between 0 and 1, Nash-Sutcliffe is between minus infinity and 1, and p-bias can be any number, any large number. So because the values are different, you need to sort of normalize them, and that's why the weights are there for. But now with PSO, this is not very efficient way. So an alternative is, instead of adding these like that, is to multiply them. Is to multiply them, and then you don't need weight. This I have already done with the objective function that exists for SPE. Sorry if you're feeling dizzy. I'm doing this. Let me go back to here, beginning the way we define here um, the multiplicative form of mean square error and the summation form of mean square error. So you see that in the multiplicative form, we don't need weights. In the summation form, we need weights. We can do the same thing with the performance criteria as in our objective function. And the reason is that if you take, this is like taking the log, simple as that. Because if you take the log of this, then it'll be this plus that plus that. So it's like taking the log. So we can multiply them. Now this one, it's in the current program, this is not implemented, but in the next version for PSO, I will implement this so you don't have to calculate the weights. We can also implement that for SPE. So you don't have to calculate the weights, you can just multiply them together. So that would be coming in the next version. So other than that, everything else is exactly the same. So as I said, this would be a short video, so I don't need to go through sensitivity analysis and all of that because I covered all of that in the previous video. So please, even if you want to use PSO, you should look at previous SPE video. Okay, at the end, let me show you something that I hope you are going to do with your project also. I really highly recommend that you try this. This is the paper that I talked about, is the fallacy in the use of the best fit solution in hydrologic modeling. And what I mean by that is that I'm going to use our project here that we just built. And I show you, if you take the objective function, the goal function here, the goal.text, and then you just copy the simulations that you made. Here I only made 80 simulations, but if you have made more, it's even better. So if you copy this file and bring it into Excel and paste it here, and all right, so this is, let me just fix this so that they line up. All right. Now, this last column is our objective function. These are all our parameters. Now I'm going to sort on the objective function. And this is what we get. Now, this would be my best simulation value. This is Nash-Sutcliffe, and these would be the parameters associated with the best simulation. Now, many people are trying to improve this. So suppose you improve your Nash-Sutcliffe, The point is that the next best simulation is significantly not different from this one. In fact, they are similar. If you run a statistical test and to determine the the level at which these are not significantly different, you probably end up somewhere very down here. 0.16 and 0.13 in Nash-Sutcliffe world is not significantly different. Now, you cannot just use this set of parameters to describe your model. You've got to choose all this because this statistically is the same as this, the same as this, the same as this. And then you look at the parameters, they are very different. They're very different. So you have to consider the p-value and the r-value to describe your model. And all the parameters associated with the 95 PPU, all the parameters that build the 95 PPU are solution to the problem that you are addressing. So please repeat this with your project so that you don't have to worry so much about satisfying the Nash-Sutcliffe criteria, which are extremely subjective when you divide it into good, very good, satisfactory, and that it's extremely subjective. You have to consider the uncertainty, and you cannot just rely on one simulation to describe a model which is highly uncertain. All your inputs are uncertain. You cannot end up with a solution which is completely certain. You have to consider the uncertainty, and for that reason, you need to focus on p-value and the r-value. There is a lot of room here to explore and to describe and to just find out what does all that mean. So I hope that you guys spend some time on this and try to explore this and make some sense out of the out of calibration of a watershed. There is a lot of room for research here. Thank you for listening.